Okay, thank you very much for the introduction. Yeah, my name is Ivan Arraut. I'm Colombian, but my PhD education was, postdoctoral experience was in Asia, as our good friend here say, I graduated from the University of Osaka. My supervisor was Yutaka Osotani, Hideo Kodama, in the KK High Energy Accelerator, where I spent the last year. ESPS postdoctoral fellow, Tokyo University of Science, CIS PI in Beijing, and yeah, short stay in Fudan and Hong Kong, and then now in St. Joseph, of course, we go wherever we can get the position and wherever there's money, then now we are there. I am going to talk about symmetry arguments for these certain problems in cosmology and particle physics. It's a collage. It's a collage about different findings in the recent years. Some of them are really published, some of them in preprints and in process, etc. Then, of course, we know that symmetries in physics are important. Symmetry is any transformation leaving a system invariant. Then, for example, if I rotate this ball around the center, of course, the shape remains the same. Different story is that if I start to deploy locally, of course, it will destroy the shape unless I introduce a gauge field, which restores the shape of the ball. So the importance of gauge fields is to restore the local symmetry. Okay, symmetry, of course, in this case, this is the diagonal group, which is just splitting the triangle around these three axes is just an example. As you know, symmetry leaves invariant the action to total derivative terms, etc. I think you are familiar with it anyway. So why symmetries are important? They govern interactions, as C and Yang claim, which is Nobel Prize lectures. Whenever the symmetry of an interaction, if you change the symmetry of an interaction, it will change completely. So symmetries are important. They tell us which quantities are conserved. They explain the behavior of a system, and we're working especially, particularly spontaneously. Of course, they are related to phase transitions and the emergence of gaseous particles, numbers from bosons, etc. Let's analyze GR. Of course, as you know perfectly, GR is pure gravity with the geometric power on the left, the short term on the right hand side with the cosmological formula here if necessary. GR has been successful, of course. We cannot challenge GR directly. In any case, if we try to modify gravity, we always have to find constraints with respect to GR because GR has so many predictions which are indisputable. One of them is, of course, the gravitational waves, which is the Nobel Prize related to LIGO observatory. It's quite interesting how LIGO challenged the uncertainty principle for the detection because they squeeze the uncertainty principle in order to be able to detect the gravitational waves. So something which didn't happen before. Of course, how do you detect gravitational waves in an amplitude 10 to the minus 21, 23? Was quite challenging before. I believe personally it would be possible. Well, of course, gravitational waves had another Nobel Prize forgotten by many people, 1974. When you have a pulsar binary system, which rotates around each other, this system emits gravitational waves. GR predicts that when a system binary emits gravitational waves, they will approach to each other at a certain rate. And that prediction was done before, even before the direct detection. So that's why people believe it in gravitational waves. They were sure that they existed. Well, we didn't detect them directly until recent. That's nice. So we also have the perihelion of Mercury, of course, GR. This another success was the first prediction of GR, which made Einstein quite happy. And well, this was before even the eclipse, no? The predictions of the gravitational lensing which came out. Gravitational lensing, of course, there is a current experiment, the density collaboration, where I have some collaborators. They are examining gravitational lensing in order to see the content of dark matter in the galaxies. Also, dark matter versus dark energy, for example, because there are scales at which they compete. They compete. So there are scales where while dark energy try to repel things, dark matter try to glue things. So there is a competition. There are scales where they start to compete with each other. And we have, of course, the dragon effect, which is another effect, in my understanding. NASA put some proof, and they demonstrated that it happens. They have to wait many years for measuring it, because, of course, the dragon effect is only considerable near the black holes. Of course, there are remaining problems. GR is not perfect. Dark matter, dark energy, the first evidence of dark matter was the flatness of the galaxy rotation curves. So when you get away from the center of the galaxy, which very, very far away from the sources, there is a distance after which you expand, and when Newton, you would expect the velocities to decrease, but instead of that, it remains flat. Well, this is logical because, of course, when Newton, Newton will decrease. Why would we expect that? Because if the objects rotate too fast, they will escape. For example, if you see the moon around the Earth, the moon and the Earth rotate around a common center. Well, let's keep the Earth fixed. The moon rotates. If you rotate too fast, it will escape. If you rotate too slow, it will fall. So there is an equilibrium condition. So the evidence of dark matter is precisely that there is no visible matter which can keep these velocities like this object should be expelled. This guy should be expelled at that distance. This was the first evidence of dark matter, and it's not the only evidence. After came many gravitational lensing and others. Dark energy is the opposite. Dark energy repels things. It is responsible for the accelerated expansion of the universe. It has a rich history because it started when Einstein formulated gravity. He believed that the universe was static. And he put a cosmological constant in the Einstein equations, which you know very well. And because he believed that the universe was static, well, which is certainly wrong because it's a very unstable. It's an unstable equilibrium. Then after Hubble discovered that the universe expands with the redshift effect now. Then in 1998, it was discovered that the universe expands accelerating. So in all span, the galaxies repel from each other, and they recede or they expand on each other faster and faster. And what is the energy generating that expansion is one of the issues. Of course, you know the history of the universe. We started with a Big Bang, a period of inflation. There was a period where light, the photons couldn't escape. Then the last scattering surface. Then there was this the period where the photons could escape, radiation dominated, matter dominated, and now we are vacuum dominated. So most of the universe is empty and it's in accelerated expansion. Dark energy represents most of the content of the universe, is almost 73 or so. Dark matter near 20 something, 26, 27, I forgot. And the other, what we know, the normal matter, plus neutrinos, is just a minority. So that's why it's so important. Why we believe that this is in agreement with the standard model of cosmology in order to keep flat the universe flatness, which is what we measure. So dark matter, of course, it will represent 30%. Dark energy is the vacuum energy portion in the universe so far. And of course, relating to the problem, this is an animation, this is what is expected, but based on the luminosity of the galaxies, Newtonian. Why Newtonian? Because it's weak fair approximation. We should expect Newton behavior, but this is what happened, the flatness of the curve. So whoever produced a theory able to explain that matter has to be able to explain the flatness, the lensing, everything. It's not only saying what is that matter, it's also explaining why the dynamics behave like that. Even if you discover a particle of dark matter, or if there is a particle of dark matter, explaining the dynamics is important. Of course, this is another picture. You have this with tendency to be flat, and this is what is expected. It's from the center of the galaxy. Remark that there's always, I cannot say always, but in most of the cases, there is a black hole in the center of the galaxy. We have one in the Milky Way. So these are the Einstein equations. Again, this is the curvature terms, cosmological constant time, the source time. If that matter exists, it would appear here in the right-hand side. But no one has seen that matter. Then what people try to 2 points of view. One is they try to modify the left-hand side or the Einstein interaction, or several problems emerge. And the other option is to investigate, to assume densities profiles of dark matter, the Navarro something profile. They invent many profiles, which are consistent with your observations. But I think the Navarro et al. Is the most popular one. Of course, we have gravitational lensing, which, as you know, is the curvature line with due to the presence of the matter. This is another picture of the same. This is the Friedman equations, of course. This term comes up to be zero when we sum out all the content units, the energy, the matter, and so on. And another issue of the matter is that the evidence of the CMBs seems to support its existence anyway. And of course, the energy, we know that there is plenty of evidence for the center of lab. And here in this talk, I will take the energy as vacuum energy, and it will emerge as the cosmological constant. So I will not modify gravity, and I will not invent any theory around. I will just try to calculate the vacuum energy density, and I will see what is necessary to do in order to obtain the right result. As you know, the main problem of the energy is the calculation of the vacuum energy density. This is the Einstein reaction with the cosmological constant plus the Lagrangian matter. This is the vacuum energy density observed, not the experimental value. Well, the theoretical prediction is this. For the calculated theoretical prediction is the integration of the vacuum energy density from the algebra of the quantum harmonic oscillator, which is the algebra we use for the quantum fields. And when we quantize quantum fields, we have to impose an algebra. Either we impose the algebra on the fields, fields and canonical conjugate momentum, or we impose the algebra of creation and annihilation operators. Either way, one will derive the other anyway. You impose the algebra in the fields, you will derive the quantum harmonic oscillator, or vice versa. You impose the algebra for the quantum harmonic oscillator, it will emerge the algebra for the quantum fields. And of course, the quantum fields, they are expanding in positive and negative frequencies, which in perfect vacuum, of course, they don't mix. When we work in QFS space-time, it's more complicated because those frequencies mix, and that's what creates the Hawking radiation, for example, and those kind of effects. Then, and of course, we know the vacuum is rich. The vacuum is rich. The vacuum is permanently creating particle to particle, electron, positron, proton, antiproton, etc. There are infrared modes in vacuum, there are ultraviolet modes. This calculation is assuming a cutoff. Cutoff now it's the Planck scale 10 to the minus 35 meters. But this like calculations have different integration. The reality is like you have this bar omega, it's 3k. Normally they take this p is k squared with k here, and this omega is k. And of course, you will have a k cube here at the end when you mix these two terms, and when you integrate k forth. And the cutoff is flat, because the max here. Obviously, momentum and space, this integration because. And then, how to say, I put Einstein because Einstein was the first guy who put the cosmological constant. Well, but of course, the theoretical calculations came after this. And this guy is 120 orders of magnitude larger than the observation. So in other words, this value is 120 zeros larger than this value. This is the worst theoretical prediction in the history of physics. And there might be many reasons for that. Of course, people can always argue about that. But the idea in this talk, of course, I will revise the calculation. I will revise some arguments about it. And the first thing I will put in mind is that the vacuum creates infrared modes and ultraviolet modes. Naturally, the infrared modes come from light particles. They have to live longer. And the UV modes come from heavy particles. They have to live less. So they have less time to when they emerge now. And the vacuum energy, we know it exists. I mean, it's not a science fiction. It's not a Marvel or so. We know it exists because we know that the Casimir effect, when you put two plates in parallel, due to the vacuum energy, they attract. And this effect has been tested several times, so we know the vacuum has energy. Another proof that the vacuum has energy, of course, the accelerators, but the fact that we can create particles from nothing when we accelerate particles in a general quantum field theory proves that the vacuum is rich. The vacuum has a lot of energy. Evidently, when we create particles, most of them are unstable and they decay. These same processes were established already. And that energy, of course, from the most basic theoretical point, we come from the algebra of the quantum harmonic oscillator. This is the algebra I was talking about. The quantum field, for simplicity, of course, on the scalar. The canonical conjugate momentum. This is somehow the extension of the position momentum, the algebra of the standard quantum mechanics. But remember that ordinary quantum mechanics is a single particle approach, where the wave function is interpreted as the probability of finding a particle. We can extend that interpretation in quantum field theory, which was the failure of the Klein-Gordon equation before. Remember when the first relativistic theory extended directly the Schrödinger equation to Klein-Gordon, the Klein-Gordon equation was interpreted as a single particle approach with unstable. And then came Dirac, who realized that the problem was in the orders of derivative. And then instead of splitting second order derivative in time theory, he used first derivative in time, first derivative in space. That solved partially the problem. And that's how the antiparticles were discovered theoretically. And then after we realized that in reality in quantum field theory, we cannot interpret whatever the functions as wave functions, but as quantum fields. And in that sense, the Klein-Gordon equation still is useful as a quantum field. And the Dirac equation, of course, is also a quantum field equation. But the key point is that what I want to remind is that even in quantum field theory, we use the same algebra of the quantum harmonic oscillator. And the algebra of the quantum harmonic oscillator always has a ground state with an energy which is different from zero. And it's this one half h bar omega. And this is the one which we show here over all the modes, obtaining the 120 orders of magnitude. Of course, this is the expansion in positive and negative frequencies, which I mentioned. And the other state comes from the Hamiltonian. When you express the Hamiltonian of the quantum field in molecular space, you have the particle number operator here. Well, if you send this to 0, this is the vacuum energy, 1/2. Of course, this term will give an infinity, which in quantum field theory is irrelevant, because in quantum field theory we exclude it. We don't care because it's irrelevant. It's just a reference point for the energy. But in gravity it matters because Einstein told us that there is an equivalence between mass and energy, equivalent mass energy. So of course the energy is a source of gravity. So wherever there's energy there, something interesting must happen in gravity. So that's why in gravity the vacuum energy cannot be neglected. And remember that in gravity we impose the Planck length. In principle, if we reach the Planck length, it's a huge amount of energy concentrated in a small point. Of course, so many things can happen at that level. Then how to solve the dynamic problem? How to decrease this 120 orders of magnitude? Or you modify gravity? Well, I work on myself and modify gravity theories for a long time. I work at massive gravity, I work at other theories. After a while, I started to abandon some of them already. Slightly agree with them. So in the recent papers, I alluded to this point. But to decrease those 120 orders of magnitude. That was my main purpose. We don't modify gravity. And starting in a simplistic approach, let's say with minimal assumptions, minimalistic, the student work. Then, of course, analyzing the interaction, of course, this integral is a triple integration with two angles and k naught. The one angle defines the plane where the pairs are placed, is theta. The zenithal angle, it comes from zenith. The azimuthal angle is which is related to the angular momentum conservation, to the angular momentum. And the other, of course, the other integral is in k, exactly. So it's a triple integral. And I was thinking, is there any way how one of those angles might be constrained? Then, of course, when I analyze let's start from the Sitter spacetime, which is this one in the Friedman method, Friedman method, Robertson Walker approach, because it's something I want to remark is that the Sitter, there are many de Sitter solutions, different de Sitter solutions. They are exactly the same, only representing different coordinate systems. Then, for example, there is the Sitter solution in static coordinates, where you have a explicit approach, which is, I think you have seen that in textbooks, is this metric, is the minus 1/3 lambda r squared, with t squared plus 1 minus 1/3 minus 1, the r squared plus blah, blah, blah. This actually is the same solution there. Because the metrics are ansatz. Let's say the metrics, what we do in reality, we make an ansatz, we assume symmetries, and we input that metric in the Einstein equations, and then impose the vacuum condition. But in the case when this cosmological constant is not vacuum, we put the lambda g mu term, that lambda g mu there, which let's put it here. You have the Einstein equations here. Minus plus is matter of convention equals 0. Of course, if this is not here, you put equals 0, and you just send this vacuum in a static. If you put this, of course, you will think this one is Sitter. Or if you do another ansatz, but in this case dynamical, then you will obtain that result there. And the ansatz, the general ansatz, in that case, is simply the minus dt squared plus a squared t, and then the r squared plus r squared the omega squared. This is the general ansatz. You put these in the answer questions, and then you solve. Yeah, but at the end, everything's an answer. Then, and that's okay, of course, it's standard, people have tested, etc. But of course, this method is equivalent to sitting in comoving coordinates. Let's say that you sit and you span with the universe. That's why you see time here so nice. And this one is static. You see all the universes. You start static and you see the universe different. Now, this metric has some set of symmetries. Well, the one I care about is the rotational symmetry. The rotational symmetry because it's the one related to the angles, and to the angular momentum conservation. And we know perfectly that we can derive a conservation law for the angular coordinates. If we use the Killing vector. This is space-like Killing vector, which is 0, 0, 0, 1. We decrease the index with the metric, and we contract it with the x mu, the top. Then we obtain an invariant, which is the angular momentum. And then, of course, that invariant will constrain the behavior of the azimuthal angle. Then let's integrate, and when you make the integration, it gives you this. Now, this exponential is a cheater. This cheats you. This R also cheats you because this R is not a variable here. I mean, it's just a parameter because you are using common coordinates. So you can just exclude the variation now. And here, H is the whole parameter. It might change in time. So this exponential could be anything also. And lambda you can take as the time coordinate, basically. Then, of course, I did an initial answer. The typical expansion we see in the textbook is this one, and I obtained this Harlow solution. Well, even this Harlow solution is telling me when I introduce I give you this, it's telling you that the ultraviolet modes, which has a very large K, they are suppressed. So they don't survive. So it means they don't cover so much angle. Yeah.
What do you mean by fine max here?
Okay, yes. Because the integration, I do the maximal angle which each frequency mode can take. Let's say when I integrate this let's say when you do that integration, the left-hand side of the bit, you have to do from 0 to some angle, which I call it max because it's the maximum possible angle, which can be taken again with the constraint generated on the right-hand side.
So we are not considering circular motion, you are considering something like scattered.
But it's like, I forgot to mention that I have to, before integrating this, I have to use the energy time uncertainty principle, of course, because energy just the kind of taking this way, and you have to integrate this such that energy, which is scaled like K, could be entered at the end of the integration in momentum space now. Because I don't work in position space. You have to translate everything in momentum space. One nice way to do is inserting the principle. The most rigorous way is Fourier transformation. Yeah.
So but not wrong, but it's not about
I don't consider, in this case, I don't care so much, but we know in a expanding universe, the energy is not necessarily concerned. Then, of course, timeline killing vectors, we use it mostly in, we can define it, of course, in this case, but mostly when I work in static coordinates, I can define a conserved quantity related to the time translations, no? But in this case, for me, was not relevant to analyze that conservation. For me, the conservation relevant was the angular. Then, for example, let's assume that you create some pairs here, electron positron. Then these pairs, they have two angles not defined. One is the plane of rotation, which is defined by theta. And then if we go in 3D, well, I should have put this in the center better for convenience. If we go in 3D, these guys also rotate. And this rotation is related to the angular momentum, and that's this phi. So since the plane of where the pairs are created is arbitrary, this theta, when I do the integration of the vacuum energy density, which is at the triple integral, the theta still is from minus pi to pi. But the phi is from 0 to phi max. And still this one from 0 from k max, which is 1 divided the planar. That's it. So the same with top, the only change is in the second integral. And then, of course, when I arrive that, I can reduce the vacuum energy density significantly. It's still, of course, if H is arbitrary, there is no perfect match with the observation, but it's a significant improvement. Now, for matching, yeah.
This is isotropic, right?
Which one?
This line item is isotropic.
Yeah.
So how will this change in phi? Because change in phi should not change the physics, right?
Yeah, you can say so. But of course, when you mix with quantum warp, where this particle, I mean, what I care is.
This is classical, right? So
Yeah, that's classical.
Due to the quantum relation, but classically, homogeneity and isotropy is respected in this measure.
Yeah, it's respected. Well, it's.
The fundamental angle doesn't take anything.
I know what you mean. Well, this is a semi-classical approach. Huh? The angle, for me, what the angle does here is to impose a constraint. The angle is related to an invariant, because the angular momentum conservation, whatever. Then, if I integrate, of course, there is a constraint. This angle is constrained by this symmetry somehow. So when you mix with the uncertainty principle, of course, you obtain something. And the idea is that in order to keep precisely that homogeneity and isotropy, of course, there is the modes have to satisfy this kind of constraint. That's essentially the idea. But yeah, I know what's your point. But it's a semi-classical approach. Of course, this is not quantum at all. It's well, of course, semi-classicals is something which we do the whole time. Hawking radiation is semi-classical, for example, and so on. So this result is published European Physical Journal actually. But I was not happy because it's not the when I computed the vacuum energy density, obviously will not give the result which you wish. Then I started to say what is the condition for the Hubble parameter, which is here, in order for the vacuum energy density to match with the observation. And it came out that it has to change like 1/T, blah, blah. But, and then of course the maximum angle is scale like this, and when it's scale like that, is when you obtain the vacuum energy density and it should be. And of course, if we see the different areas of the universe, well, so you can do it by yourself. Because H is A dot divided A. H is A dot divided A. If you do it for different areas, radiation, matter, and whatever, you will obtain precisely this kind of dependence, 1/T and something. Then it seems that the Hubble parameter change such that we obtain the cerebral angles, which of course is not this, it finished being this. And then of course, when you do the deeper integration, for example, you do the vacuum energy density calculation, you have this triple integral here. Then you have I will put K immediately because it's H bar omega finish. This here will be the 3K, but this 3K is K squared. I think sine theta, theta 3 or something like that. If I didn't make any mistake. So the first integration will be theta minus pi to pi. I don't change that because this is the plane where the particles are created. What I change is this one, 0. Well, this is scale like 1 over k squared with some parameters. And this is 0 to k max. Naturally, when we study calculus 3, it's a simple integration of calculus 3. So the first integral gives you 2, and a factor of 2. So with the second integral is irrelevant because it's I forgot the k here. The k is relevant if I don't if this is 2 pi here, this will obtain exactly the 120 orders of magnitude. Well, what happened now is due to the constraint, this is 1 over k squared. So at the end, when we study calculus, we know perfectly that the upper limit, when we integrate by these double and triple integrations, we have to replace the limit. And this suppresses naturally this will be k, and then k squared with some factor. And this is exactly what happens, what is perceived in the observations. I mean, if you see, for example, this is the integration. By yourself.
Your whole parameter is one p.
Yeah. Plus some constant or something.
Yeah. In intelligence, the scale factor is approximately the t. The scale factor a t is approximately t, just t, medium fundamental t.
Okay. Scale what?
A t.
Your scale. Yeah, AT. The scale factor. You mean scale factor. Well, you can replace up to some factors. You retain different factors. But for example, this radiation. This is how radiation depends in time. The factor. This is in matter dominated. And so on. Then if you in curvature, well, in all of them, if you replace here, you will obtain something like this. Some factor divided t and so on.
Yeah.
Then
the scale factor AT increase.
Yeah, exactly. AT, exactly. Is what?
So this is your background. The photo study, this could be the background or your photo study.
Well, I hope, sorry, I probably download. Let's say my understanding is that you say that, of course, the scale factor, yeah, whatever it is, it will be something divided t. Then, of course, initially, I don't care what is this factor. I just care by 1 over t something. And whenever I replace the 1 over t something, I obtain something which is scale exactly what is observed experimentally for the vacuum energy density. Then there must be something right in that direction. It's too much coincidence that the whole parameter has to change like that, precisely for obtaining the vacuum energy density like that. Then that's why I believe that probably could be the right direction for solving these problems. Then of course this is the interaction. I think I copied well, yeah. Then it's a strong suppression of short wavelength modes. Then let's analyze the phenomenology. I think there's a picture here, yeah. The phenomenology is like this. You have a particle and a particle, no? They are created, or when they are created in vacuum, of course we cannot see them. Not even particles we can see, so much worse if those particles are created and annihilated in all time. But the particles are created in an arbitrary plane. Yeah, that arbitrary plane is theta, so we don't know. We have to show all the possibilities, theta, from -5 to pi. But those particles, they appear in a very random way. They have to rotate around each other. So if these particles comes from light modes, very light, they live longer and they have more time to circle around each other. So they cover more angle and they contribute to the integral. But the ultraviolet modes, the come from heavy particles, they live less. They don't have enough time for covering the angle, so they are suppressed. This is more or less interpretation I give to the phenomenological interpretation to this result. Of course, the first publication was this, which was recently featured by the editorial board. This one, but in this one, my proposal was to explain how the cosmological constant can emerge from symmetry bias. From symmetry, I was not thinking this calculation. And subsequently is where it can see zero physical energy, where I do the calculation, including the Friedman elevator Royce Walker, etc. Because initially I'm wearing static coordinates, and the referees always complain that why you don't use the Friedman or something. I always explain the same but different coordinate system. Well, anyway, the point is that it seems to be the right approach. Now, I will jump now. I will abandon that problem. I will go to dark matter.
No problem in the previous presentation.
Huh?
So it was, the static coordinate means that the static distance was static, right? We must keep it.
No, static coordinates is like this one. Yeah.
Really?
Yeah, of course. If there's consistency, this calculation should emerge also from static coordinates.
Seems like the process happening in the spatial slice. So I feel like watching it is broken here.
I mean, here the background space time is already this time.
So then I don't know how you can compute in terms of Fourier mode. To have Fourier mode, then you have something depending on the spatial coordinates as well. I mean, x, a function which depends on x, not on time. Then only we don't have this energy in terms of moment Fourier modes. Right?
Yeah, that could be defined only in the static cache or static coordinate.
So then it gives the homogeneity, right?
Homogeneity.
I mean, unless the
Yeah. And how can convert the argument from the argument of the law?
I don't want.
I was giving you static coordinates.
No. What I mean is that I did the calculation initially in the static coordinates, and then subsequently I did in Friedman relator also. For static coordinates, there are some problems with the interpretation. It's not that clear. In Friedman elevator also work is more transparent, the interpretation. So, of course, the symmetries considered in both cases are different, but still you can define an angular momentum in both coordinate systems. So, only another difference is that in static coordinates you use the momentum position uncertainty principle as the way to translate from in order to execute the integration in the momentum space. But in Friedman elevator Royce Walker, since it's dynamics, you are more concerned about the energy time uncertainty principle. And the radial coordinate is more decoration. It's like a decorative, it's like a luxurious device which you carry. Of course, you can consider relative motions with respect to you sit with the universe, you can move also relative to that, but I don't consider that as case. Because what I care is the vacuum, how the modes behave when they are created and destroyed in the vacuum. I mean, the pairs. Any other questions so far?
You start with the angular rotational symmetry, but your momentum integral breaks rotational symmetry. And so when to the concentrated near 5 to 0 or large enough cage.
Which momentum integration, sir?
Angular undercut, yeah. 5 meters becomes very small for large cage, and you break the rotational symmetry. Yes.
Well, that could be that there's a reason for that, because of course, even if you start with this constraint and so on, and this, after you combine, this is a classical calculation, of course. Well, after you have to include the quantum arguments. The quantum arguments were introduced naively via uncertainty principle, of course. In a more rigorous way, you could use Fourier transformation you want. So that could explain probably your question about why it breaks the so-called rotational symmetry. It's not exactly, well, take into account that the virtual particles are weird, no? They also violate the energy conservation partially, because when they emerge, they are stealing energy somehow. But it's part of the uncertainty principle. The uncertainty principle precisely is a partial violation of the energy conservation. Then there's no strange that it's a partial violation of rotational symmetry here, precisely for the nature of the quantum of the virtual particles. Then well, this is a good comment. It's something to analyze further subsequently. So far, any other comment? So then I jump to dark matter now. I abandon dark energy. In dark matter, I have more problems. I have more problems than with dark energy. Because dark energy, I didn't invent anything. Actually, there's nothing new. It's just vacuum energy. And what I did is to impose a constraint and use, I mean, all the arguments are standard, no? Well, in that matter, I started to mess up a little bit the things. Then first I proposed a solution here. It was a little choice in time. It received a comment. I replied to the comment. The comment was partially right in the sense that the metric proposed here is not exactly vacuum, but it was wrong in other things. I improved the solution here and here in this modification. And what I did is to change the symmetry at galactic scale somehow. Again, rotational symmetry. Then let's talk a little bit about symmetries. Of course, symmetries. This is the standard Basel metric. And normally we have, if we calculate geodesics, we have this mess. But luckily, fortunately, when we use the symmetries, everything becomes nice. We have a parallel Killing vector, we have the rotational Killing vector, which I mentioned before, and these are the invariants. Huh? Of course, we have to download the index here with the metric and so on. This is how we obtain the energy conservation in spatial and the angular momentum in spatial. And this is just the equation of energy, which is here. And when we impose this conservation laws, of course, we simplify the equation to this. Equal to a constant, this is kinetic, this is potential. And everything depends on how this potential behaves. Nice. GR, again, of course, was successful is because it could introduce this term. This term, actually, until what time is the seminar? Sorry, I don't want to use the. Until what time is the?
10 minutes left.
Really? Oh my God.
Yeah.
Okay. Okay, I will cover until I can. Okay, this is usually the potential in standard GR. And GR was successful because of this term, the coupling between master and angular momentum. Of course, you know this part is trivial. Then I try to affect the symmetries at galactic scale, the rotational symmetry in particular. And my purpose was to derive the coefficient law, which is well established. The scales of dark matter, which we know that they occur, dark matter occur when in the geometric average between the gravitational radius and the inverse of some acceleration parameter, which is actually the finished being the scale of the universe. No? So, and this scale, of course, comes from the theories of Miller and Bekenstein, modifying Newtonian dynamics. But any attempt to reproduce with modified Newtonian dynamics in a relativistic way was inconsistent, so I tried to avoid those approaches. This was my initial approach, which was not, I didn't like so much at the end, but this was the initial idea, was to convert this solution by imposing the tangential velocity as invariant instead of the angular momentum at galactic scales. Then, of course, that solution obtains this equilibrium condition and obtains the Fisher law. But I obtained this as an effective potential, but still the challenge was lengthy. Then I tried to improve it. And then I went further. And what I did is to propose this Ansatz metric. Instead of scaling R squared, here is theta R. Of course, this can converge to a vacuum if we do a redefinition or a scale of R and so on. But if we impose the tangential velocity as the invariant regarding the scales, and I'm talking about this kind of, which normally was the normal, well now it will be the tangential velocity, or proportion, something proportion. Then imposing that and keeping it for any coordinate system, I obtain this method, which is a vacuum method which can converge to vacuum under some transformations, plus some redefinition, and plus the change of symmetry. And this is the potential. And this potential, of course, can derive the Fisher law and the scales. The equilibrium scale corresponds to the scale of dark matter. And why we believe these are the scales of dark matter? Because if you replace the baryonic matter inside this scale, forget this scale. These are the values of different galaxies, Messier, blah, blah, blah. And all these values match with the scales where dark matter has the strongest effect. So, of course, there's an observational reason for that. Remember. And then I went further because, of course, it's not enough. The fact that the tangential velocity is the conserved quantity guarantees the galaxy rotation curves. The flatness of the galaxy rotation curves is guaranteed because the tangential velocity is invariant. But how to reproduce lensing? Then I established something recently, the dynamical origin of dark matter, is when you go to the weak field approximation of the Einstein equations, the zero components are developed, and this is the equation vacuum, and this is how the metric becomes a general vacuum condition. Then when I convert my solution to the spatial case, you obtain a vacuum condition like this. This is the vacuum, a spatial light vacuum, let's say. This is the new vacuum, of course, also, of course, locally. But the problem is when we use the metrics or the star, when we start to compare the two vacuums. And when we start to compare, there's a discrepancy. And of course, if we use the Laplacian defined in the spatial light case, with the solution obtained in the new solution, you obtain a density profile. And that density profile scales like that, like 1 over R to the phi 2. It's not exactly in a Navarro profile. And by the way, C1 is negative, though. That's why there's a minus here. This is not exactly the density. The Navarro profile goes to 1 over R cubed at larger scales, but it's quite close. Actually, it's quite close because 5 divided 2 is 2.5. So phenomenologically, might have some implications. So from my perspective, that matter might emerge dynamical for the comparison between two vacuum solutions with two different symmetries.
Could you explain more about the skill check?
Which one? This one or this one? This one.
Yeah.
Which one? Okay, this is the Laplacian, but the Laplacian changes with the metric you use. Let's say, for example, in each metric you have to redefine the Laplacian. In a spatial light, there's 1 over R squared here and there's R squared here. But in the other coordinate system, let's say in the metric scale different, you have to change consistently how these factors scale. And of course, even if you replace the new solution with the new factors, and still you obtain a vacuum solution. It's a delta derivative at the end, which is the standard case. But when you use this definition of a flasher with the new solution, of course, you will obtain some density profile. So it's equivalent. Let's assume when we analyze, unfortunately, I will not be able to cover that, but when we analyze Hawking radiation, for example, you
Monde theory. This one is
no, it's not MOND. Actually, I use MOND as a reference. Modified Newtonian dynamics is a reference because it has some positive things. It has the scales of dark matter. It has one parameter which tells us when it happens, etc. But I use as a guidance, but it's not the theory because I don't modify gravity neither. It's just symmetry arguments. Actually, everything is symmetry arguments. Then I don't know if I will be able to cover because it's also another issue is that, for example, in my Hawking radiation, when Hawking derived Hawking radiation, what he did is to compare two vacuums, one before the formation of the black hole with the vacuum after the formation of the black hole. He connected via Bogol-Wolff transformation. Here, there's comparison also vacuums go in a different way, a classical way. This comparison is classical. In other words, if we use our tools now and our metrics, our standards of metrics for trying to analyze a solution, which doesn't follow those metrics, we will obtain a density profile. And of course, we will obtain the lens, the enhancement of lensing, and all these kind of things. But if we switch to the appropriate metrics and the appropriate standards, then we will see a vacuum solution. It's more or less the standard idea in this case of dark matter. Any other comment or question? So of course, some of these results are published, some of them are published, some of them are in process, some of them are eventually one other rejection, which is quite normal in physics, but of course, still there are a few published. And of course, people might have different opinions about this kind of comparison. Now, I don't know if I have time, but maybe 5 minutes, if you don't mind. I will jump a little bit further. I will not explain this part because you know this part. In the past, I did a connection between quantum gap and Gaussian theory, which I will not explain, but I will have gone to Hawking. Recently, I also formulated the Hawking radiation as a mechanism of spontaneous symmetry. This is the Lagrangian, able to generate the same spectral radiation of Hawking. It has a quadratic, cubic, and quartic term, the particle number operator. N is a dagger, of course. And you find the vacuum condition of this operator when m squared is larger than 0 is trivial, when m squared is smaller than 0 is non-trivial. So it means the particle number operator is another parameter in the Hawking radiation. And Hawking radiation only appears when the symmetry is spontaneously broken. So it means the black hole is always permanently trying to find a stable equilibrium, but it fails. So because it's breaking the symmetry at a given time, it breaks the symmetry spontaneously, and the big pattern with symmetry, the symmetry related to the internal configuration, which keeps invariant the mass, charge, and angular momentum. So, which is related to the no-hair theory. So at the end, remember that Hawking compared to vacuum. So the idea came like this: Hawking expanding a quantum field, positive and negative frequencies. This is before the formation of the black hole. This is after the formation of the black hole. Some modes go inside. We don't care. We care the modes which escape. And what we do is we define a vacuum locally before the formation of the black hole and a vacuum locally after the formation of the black hole, and we compare them via Bogol-Wolff transformation. And again, when we compare the two different vacuums, for example, if I use this operator in the wrong vacuum, I will obtain particles. And that's what Hawking derived basically. And then at the end, since the particle number operator is the only parameter, of course, the superposition is very well known that the other parameter, right? Just through it over all the possible growing states, it gives you a trivial result. This is a very standard result when established in physics. Before the symmetry, before you select a growing state, before the symmetry is broken, the vacuum you have not selected, you choose all the possible vacuum states, all the possible other parameters, and you will obtain 0. Then if the particle number operator obeys this, it means that there are some particle number which is called negative, and how to interpret them, maybe particles moving in the opposite direction, maybe antiparticles, etc. Consistent, of course, with the picture of Hawking that the pairs are created, some of the enter. And of course, there are some a couple of publications in that direction, where I am trying to attack the black hole information paradox, but I cannot solve because there are many things to consider. And finally, I am also concerned with the neutrino oscillation problem, which is a problem which a friend from Fermi wrote to me for recently. Of course, it's not that I am the only one attacking it. There are many people doing it. But again, I want to do a simplistic approach, only with 3 flavors. My results was based initially in the triangular formulation. This is the standard approach. These are the mixed angles. This is cosine theta 1, 2, theta 1, 3, blah, blah, blah. Then the approach which I did is to define 3 ground states, 3 vacuums corresponding to the 3 different flavors. And the picture suggests that when the neutrino flies, it shifts different vacuums from monic, chaotic, and electronic. But it never selects one. It never breaks the symmetry spontaneously. Then that's why I take the flavor as another parameter, and I find some constraints. And interestingly, those constraints are consistent with observations somehow. I don't know if a coincidence or not. And finally, I obtain some constraints by using some triangular formulation between the mixing angles. But the triangle is an approximation because it's not perfect. And the result suggests it's normal hierarchy, not inverse hierarchy. Normal hierarchy is that I don't know if you're familiar, I didn't have time to explain the neutrino so much, but normal hierarchy is that there are 3 masses. The mass 3 is much larger than mass 1 and mass 2, and the other mass 1 and mass 2 are very close. So whoever is familiar with the problem will know. And this is, okay, I have YouTube channel, follow me. And then if you want. And my conclusion is the neutrino mass, I have not generated any mechanism for the neutrino mass. This is the major complaint of the reference. Author one paper is almost published already. Another was rejected. But the complaint is that I have not written explicitly a Lagrangian for the mechanism generating the neutrino mass. Still, what I found is some constraints and some physical feature for constraining the parameters related to the oscillation. I didn't study quantum Jabasser, but I demonstrated in the past that there is a correspondence between quantum Jabasser equations and the dynamical theory. So solving the counting problem, when you want to condense matter system, 2 broken symmetries can generate only 1 Nambu-Goldstone bosons, and the frequency could be quadratic, which is not what happened in high-energy physics, which a problem. It was a problem attacked by Murayama and others in the past, and in the Nielsen and Chada, and Yoichiro Nambu inside. And then the black hole information paradox might be solved by symmetry argument. Observe cosmological constant bounds obtain the asymmetry constraint and the effects attributed to dark matter. From my perspective, emerge from deviations of spherical symmetry and by comparison of vacuum states. And this is my talk today. I have to accelerate at the end because thank you very much.